Why does a truck need several braking systems when a car uses only one? At first glance, braking a vehicle seems quite simple. You press the pedal and the vehicle slows down until it stops. This principle works well for cars and light vehicles that travel on roads every day. However, when observing the operation of a heavy-duty transport truck, the situation changes completely. A long-haul truck can carry a load that multiplies the weight of a conventional vehicle many times over, and when fully loaded, the unit formed by the tractor and the trailer can reach dozens of tons. Moving that mass already requires a large amount of energy, but stopping it safely involves an even greater challenge. To understand why this happens, it is necessary to see what occurs every time a vehicle reduces its speed. When that happens, the energy of its motion must be transformed into another form of energy, and in traditional braking systems, that energy is primarily converted into heat. In a car, the braking system is designed to handle this process during normal trips. However, when dealing with a loaded truck descending a slope for several miles, the amount of energy that must be dissipated is much higher. Under these conditions, using only the braking system that acts on the wheels would not be enough to maintain control of the vehicle throughout the entire journey. If that system were used constantly to reduce speed on long descents or demanding routes, the heat generated could affect its efficiency and compromise safety. For this reason, trucks are designed with different systems that help control speed in various situations. Some are designed to stop the vehicle when necessary, while others allow for speed reduction without continuously depending on the main brakes. There are also systems that help maintain control of the truck on prolonged stretches, where gravity constantly pushes the vehicle forward. When all these systems work together, the truck can maintain a safe speed even in demanding conditions, avoiding the overloading of a single braking mechanism. But this leads to a fundamental question that allows us to understand how the entire system works. If trucks already have brakes on the wheels, why do they need additional systems to control speed? The answer begins with the system that remains responsible for stopping the vehicle, the brakes that act directly on the wheels, which constitute the primary mechanism for braking a truck. This system is known as the service brake and comes into operation when the driver presses the brake pedal in the cabin. Although trucks use other systems to help control speed, the service brake remains responsible for providing the necessary force to reduce speed or stop the vehicle completely when required. To understand how that braking force can be generated in such a heavy vehicle, it is necessary to observe a key difference compared to cars. In trucks, braking force is not transmitted in the same way as in most light vehicles. While the latter use hydraulic systems, trucks employ compressed air in a system known as a pneumatic brake system, designed to function reliably in vehicles that may have multiple axles and carry very heavy loads. The use of compressed air allows the braking force to be transmitted uniformly throughout the entire vehicle assembly, which is especially important considering that a transport truck is not just the tractor unit. The trailer also has its own brakes, and all these mechanisms must be activated in a coordinated manner to stop the entire assembly stably and safely. For this entire system to work, the truck must constantly generate and store compressed air while in motion. The process begins with the air compressor, a component connected to the vehicle's engine that is responsible for producing the compressed air needed for the system. The generated air is stored in tanks designed to maintain constant pressure, allowing the braking system to always have the energy necessary to act when the driver presses the pedal. When the driver presses the brake pedal, the system releases part of that air pressure toward the brake chambers located at the wheels, where a mechanism transforms the air pressure into mechanical movement. This movement activates the components of the braking system that press the friction surfaces against the elements that rotate with the wheels. When those surfaces make contact, the rotation of the wheels begins to slow down. The friction generated converts the energy of the truck's motion into heat, allowing the vehicle to decrease its speed progressively. This process occurs simultaneously on multiple wheels of the truck and the trailer, providing the braking power necessary to control a high-mass vehicle. This coordinated action on multiple wheels is precisely one of the most important advantages of the pneumatic system, which has the capacity to act on several axles at the same time in a vehicle that may have numerous braking points distributed along the tractor and trailer assembly. When the system is activated, the air pressure is distributed through control valves and reaches each of the brake chambers so that all wheels contribute to the braking process. The power this system can generate is considerable. Even when the truck is fully loaded, the service brake is capable of stopping the vehicle effectively when conditions require it. However, that same power has an important consequence when used for prolonged periods. This is because every time the wheel brakes reduce the truck's speed, a large amount of energy is transformed into heat, which in normal journeys dissipates without causing problems. But when the vehicle must reduce speed for long periods, such as during prolonged descents, the accumulation of heat in the system can increase rapidly. This phenomenon introduces a significant limit on the continuous use of the service brake because although the system has the capacity to stop the truck, relying exclusively on it to control speed in all situations can generate conditions that affect its performance. That limit is not due to a weakness in the system, but rather the way the braking process itself works in such a heavy vehicle. The reason lies in the physics of braking. When a vehicle moves, it possesses a certain amount of energy associated with its speed and mass. The heavier the vehicle and the faster it moves, the greater the amount of energy it carries. To reduce speed or stop the vehicle, that energy must disappear in some way, and in traditional braking systems, the process consists of transforming it into heat. This transformation occurs through friction, which appears when the braking system is activated, and the friction components press against the surfaces rotating with the wheels. This contact generates resistance to movement, and as the wheel tries to continue rotating, friction converts the motion energy into heat that accumulates in the discs, drums, and other elements of the system. In a car, this process occurs with a relatively moderate amount of energy because the vehicle's weight is lower and braking events are usually brief, so the system components are designed to dissipate the heat generated during these situations without braking performance being affected. But in a loaded truck, the situation is very different. The total weight of the vehicle can be several times that of a car, and at the same speed, a vehicle with greater mass carries much more energy, meaning that every time the truck reduces its speed, the braking system must transform a much larger amount of energy into heat. When braking is short and spaced out, the heat generated has enough time to dissipate into the air circulating around the components. However, on prolonged descents, the driver needs to keep the speed under control for several minutes, while gravity constantly pushes the truck downhill. If only the service brake were used to maintain that speed throughout the descent, the system would be generating heat continuously, and as the temperature of the components increases, their ability to produce friction begins to decrease. The result is that the braking system needs to apply more and more pressure to produce the same braking effect, and if heat continues to accumulate, the system's performance can be considerably reduced. For this reason, relying solely on the service brake to control a heavy truck during prolonged descents would not be a safe strategy. One of the most important systems that makes this possible uses the truck's own engine as a source of resistance to movement. This mechanism is known as the engine brake and is a fundamental part of speed control in heavy transport. To understand how it works, it is useful to remember the normal role of the engine when the truck is accelerating. During standard driving, the engine produces energy that is transmitted to the wheels through the transmission, pushing the vehicle forward and allowing it to maintain or increase speed. When the engine brake is activated, this operation is partially reversed. Instead of generating power to move the truck, the engine begins to offer resistance to the movement coming from the wheels. Because the wheels continue to rotate as the truck moves forward, that movement is transmitted backward through the transmission system and forces the engine to keep turning. At that moment, the engine stops acting as a source of momentum and begins to behave as a system that absorbs energy from the vehicle's motion. This mechanical resistance gradually reduces the truck's speed without the need to constantly use the wheel brakes. For this reason, this principle is especially useful on prolonged descents, where gravity continuously pushes the vehicle downhill and the driver needs to keep the speed under control for long periods. If they relied solely on the service brake to achieve this, the braking system would be working without rest throughout the descent. In these situations, the engine brake fulfills a key role within the general braking strategy of a truck. Its main objective is to reduce the vehicle's speed before it becomes necessary to apply the service brake, so that the main braking system can be reserved for situations where a faster reduction or a complete stop is required. Thanks to this system, the truck can maintain a stable speed during demanding journeys without subjecting the wheel brakes to constant effort. This contributes to extending the life of the braking system and reduces the risk of overheating in difficult conditions. Even so, in certain driving conditions, even the engine brake may not be enough to fully control the speed of such a heavy vehicle over long periods. To face these situations, some trucks incorporate an additional system capable of generating resistance to movement without resorting to the wheel brakes or depending solely on the engine. This mechanism is known as a retarder, and it performs a very important function when the vehicle must reduce speed over long periods of time. Unlike the service brake, which acts directly on the wheels, the retarder works within the truck's transmission system. Its goal is to generate resistance to the vehicle's movement before the energy reaches the main brakes. In this way, part of the energy pushing the truck forward can be absorbed within the vehicle's own mechanical system. The general principle of the retarder consists of transforming the truck's motion energy into another form of energy within a mechanism designed to withstand that effort. By generating this resistance, the system helps reduce the vehicle's speed or keep it under control without the need to continually apply the service brake. In many heavy-duty transport trucks, this system takes the form of a hydraulic retarder. In this type of device, a set of components rotates within a special fluid. When the retarder is activated, part of the mechanism begins to rotate, driven by the movement of the transmission, forcing the fluid to circulate within the system. That movement generates resistance to the rotation of the internal components, acting as a force that opposes the vehicle's progress. As a result, the truck begins to reduce its speed or maintains a constant pace even when the road descends. During this process, the energy of motion does not disappear. It must be transformed into another form, just as in other braking systems. In the case of the hydraulic retarder, much of that energy is converted into heat within the system itself, and retarders are designed to dissipate it in a controlled manner, allowing the mechanism to operate for prolonged periods without affecting the main brakes. This feature is especially useful when a truck descends a mountain road for several miles and the driver needs to keep the speed under control without constantly resorting to the service brake. Instead of depending solely on the wheel brakes, the retarder can absorb part of the motion energy, allowing the brakes to remain much cooler and available for situations where more intense braking is truly needed. In many modern trucks, this system does not work in isolation. It is usually used together with the engine brake to generate progressive resistance that maintains control of the vehicle during the most demanding journeys. While the engine brake reduces part of the speed through the engine's internal resistance, the retarder can provide additional force that helps stabilize the descent. The combination of these systems allows the truck to control its speed over long periods without subjecting the service brake to continuous effort. This not only improves road safety but also reduces the wear and tear on the components of the primary braking system. The result is a much more efficient system in which different mechanisms work together to handle the enormous energy associated with the movement of a heavy vehicle. But understanding each system separately is only part of the story. The real question is how they are used together during driving to keep a truck that can weigh dozens of tons under control. In practice, driving a heavy transport vehicle is not simply about accelerating and braking when an obstacle appears, because a large part of the driver's job consists of continuously managing the truck's energy. Every time the vehicle gains speed, it accumulates a massive amount of energy due to its mass, and controlling it safely requires using different mechanisms at the right time. This control usually begins with the systems that generate resistance without directly using the wheel brakes. When the driver needs to reduce speed progressively or maintain a steady pace on a slope, the engine brake becomes a fundamental tool. Upon activation, the engine itself begins to offer resistance to the truck's movement and helps reduce speed gradually. In many modern vehicles, this effect can be reinforced through the use of the retarder. This system absorbs part of the motion energy within the transmission and contributes to generating additional resistance that helps maintain control of the vehicle. By acting alongside the engine brake, the retarder allows the truck to descend long slopes while maintaining a constant speed without the need to continually use the service brake. This style of driving has a very clear objective. By first using systems that generate mechanical resistance, the workload that the wheel brakes must endure is reduced. In this way, the main braking system is reserved for situations where the driver needs immediate intervention, such as when an unexpected obstacle appears on the road or when it is necessary to sharply reduce speed before entering a tight curve. In these types of situations, the service brake comes into play, as it remains the most powerful system in the set because it is the only one that can directly apply a large frictional force to the vehicle's wheels. When the driver needs to reduce speed quickly or stop the truck, this system provides the braking capacity necessary to control a mass of several dozen tons in a very short time. For this reason, the service brake is reserved primarily for specific interventions where immediate deceleration is required, while the auxiliary systems allow for the continuous management of the truck's speed during prolonged journeys. In practice, vehicle control is based on the combination of several mechanisms acting complementarily. While auxiliary systems generate resistance to keep speed under control for long periods, the service brake remains available for situations where more intense braking or a full stop is needed. Thanks to this combination, trucks can transport very heavy loads and keep speed under control even in demanding conditions. What at first glance seems like a set of redundant systems is actually a carefully designed architecture to manage enormous amounts of energy efficiently. In vehicles of these dimensions, controlling movement over thousands of miles requires more than a single braking system. That is why trucks use several mechanisms that work together to maintain stability and control in all types of situations. Understanding how these systems work allows us to see heavy transport from another perspective. Behind every truck on the road, there is a combination of engineering, physics, and design intended to control a massive amount of moving energy and turn it into something as everyday as a vehicle moving safely down the road. If you are interested in these types of technologies that normally go unnoticed, you can subscribe and leave a like so that the YouTube algorithm recommends this content to more people who enjoy understanding how machines and the systems that make modern transport possible truly work. Because behind every truck you see on the road, there isn't just a vehicle transporting goods. There is one of the most complex and important machines in the infrastructure that keeps the world moving.